So we've looked at the general equations of simple harmonic motion. We've looked at one specific example, that's mass spring systems. Okay, now we've got to look at another specific example. This is the pendulum. Okay, so a pendulum is just simply some fixed point, a string with a mass on it, swings forwards and backwards. The first thing we need to think about is what might affect the period of that pendulum, the time it takes to complete one swing. The first one, which might seem sensible, is the mass. Of course, the mass did affect a mass spring system, right? Because there the force was coming from the spring, and the force would be the same with the same extension, but on a bigger mass that would cause a smaller acceleration. So the mass did affect the period. With a pendulum, though, the force is coming from the actual weight of the mass itself. And a bit like a falling object, remember we can have a small falling object or a big falling object. We drop them, they both fall with the same acceleration. Right, this is also true for a pendulum. So the mass has absolutely no effect on the oscillation, the period of the oscillation at all. The second thing is the amplitude. So you might think that a big swing compared with a small swing would make a big difference, but if you pull a pendulum back to here and let it swing like this, compared with the pendulum that you just pull back a tiny little way and let it swing forwards and backwards like this, that actually does make a very small difference, but only a very small difference, because remember that one of the things we showed with SHM is that the amplitude doesn't affect the period. Okay, it turns out when we do the derivation next lesson that's not quite true for a pendulum. It will have a slightly different period when it's got a longer amplitude, a bigger amplitude, but it doesn't make a very big difference, and for small oscillations we can ignore that effect. So the third thing that affects it is the length. Okay, there is a big difference between a short pendulum and a long pendulum, right? But so we know the length affects it, but the question we're trying to sort out in this lesson to see if we understood this log kind of analysis that we talked about is that depends on the square root of the length, the length of the 3/2, the length squared. Okay, what is the way that the length affects the period? So if you've understood the idea of logs, you can see how we're going to sort that problem out. Okay, because what we've got is, we know that the period depends on the length, but it depends on the length to some power n and with some constant k, and our job really is to identify these two numbers, n and k. Okay, so if we've learned this properly from mass spring systems, okay, you'll know how to solve this problem. So the technique we do is we do exactly the kind of experiment you'd imagine at GCSE. So we work out we do some different lengths. So we do a nice range of lengths. We time 10 oscillations. We divide that by 10 to get the time for one oscillation. Okay, but in the past what we've said is, this is the kind of GCSE way. We'd say, well, let's plot T against L. T against L will give us some sort of relationship like this. So we want a straight line. So somebody in the past would have said to you, well, okay, let's plot T cubed against L, or T against L squared or something. Let's see how to make a straight line graph. What I'm saying to you now is, well, I'm not going to tell you that. I'm not going to tell you how to make a straight line graph. Okay, but you do have your relationship, so you know that T equals K L to the N. What are you going to do? Well, you're going to plot a log-log graph. So this is the log base 10 of the length. This is the log base 10 of the time. Okay, notice the numbers look a bit confusing here. All these numbers are negative because these numbers here are less than 1. And the log of any number less than 1 is a negative number. It doesn't mean the number's negative, just the log is. The log of the period goes from being negative to positive, but that's just because the time has gone from less than 1 second to more than 1 second. Right, that does make the graph a little bit difficult to plot, but it's still basically the same sort of graph. So this is the sort of graph that you end up with if you plot that data, a straight line graph. Okay, notice crucially on this graph that I do have an x value for naught here, so I can just read the intercept off the graph. So here's my intercept, 0.3. Okay, I can then find the gradient. Okay, and the gradient of the graph is 0.5. So the crucial thing we need to be able to do then is to relate this equation. How does it tell us the values for this equation? Okay, this is how it's done. So we start off from T equals K L to the N. Take logs of both sides, and then we need to be remembering our log rules. So remember, our two log rules here are log of AB equals log A plus log B, and the log of a to the n equals n log a. Okay, if you know those two log rules, then you can split this thing here, split that apart. So we get log of AB. So first of all, we get, this is our one thing, this is our other thing. So the two things multiplied together. Okay, the logs, you have to add the logs. And then we look at our log of L to the n, and that becomes n log L from our second log rule here. And then just to tidy it up, we turn that round. So we get log t equals n log L plus log k. Well, if you remember, what we just did is we plotted a graph of log t against log L. Okay, if we do that, and we get a straight line, okay, I know the axes were in different places, but still the same principle. This would just be some longer lengths, more than a metre long. Okay, what we can do is we can relate this to this, and of course that's a straight line graph, so it's in the form y equals mx plus c. Okay, where the y was log t, the gradient was our value for n, x was log L, and c was log k. Okay, this was the equation we got from the graph. Okay, so n is easy, it's just written there as the gradient of the graph. The bit where sometimes people go wrong is that 0.3 isn't k. Okay, it's log k equals 0.3, so you have to go k equals 10 to the power 0.3, which was 2. So the equation linking the period to the length of a pendulum is t equals 2.0 L to the 0.5. Okay, just a little bit about the experiment. When you do it, you might not get a value of 0.5 here. You might get something like 0.48 or something, would be quite a reasonable value to get. Okay, but this will tend to be a whole number or maybe a half, like this is, but it won't be something like 0.48, okay? It'll be a square root, a squared, a 3 over 2 maybe, that kind of power, not a number like 0.48. This number here, though, this is just coincidence, really, just to do with the numbers that we happen to use in our system of units, that this ends up being fairly close to 2, okay? Because that would depend, so for example, if you went to do it on a planet with a different gravity, that would be a different number. But the power here is usually an integer or a half. So that's empirically how we get the relationship between the period of a pendulum and its length. Okay, empirically means just by doing it by experiment.